for, well, the opportunity to give this talk, and also for the flexibility in terms of scheduling and dates. So I do appreciate that. So, okay, so I'm going to talk about the linearized conformal Einstein field equations around Petrov-type D backgrounds. And this is a work that I did in collaboration with one of the founding members of the Hyperboloidal network, Rodrigo Panoso Macedo, and also another dear Hyperboloidal friend, Justin Feng. So probably with this audience, I don't have to give too much motivation on why it is important to include null infinity and about conformal transformations, but let me use this slide just to set up the notation. So in Penrose's proposal, so instead of looking at the asymptotic region of the physical spacetime with physical metric G tilde, so what we do is to make a conformal rescaling of this physical metric through a conformal factor to obtain the unphysical metric. So the notation is physical fields will have a tilde, while unphysical fields, or the rescaled ones, will not have a tilde. And we all know what are the equations satisfied by the physical metric. In vacuum, they read Ricci physical, so Ricci tilde, is equal to lambda times G tilde. And so it's a straightforward calculation to check that if you make a conformal transformation of the metric and you compute how the unphysical Ricci relates to the physical Ricci, you find this expression, which contains second derivatives of the conformal factor and these 1 over the conformal factor terms. And the region we are interested in studying is the region where the conformal factor vanishes, that's the conformal boundary. And this means that this equation is formally singular. And here I want to just spend a word on saying what formally singular means. It simply means that your eyes, the photons reaching your eyes, see a 1 over conformal factor term, right? Formally singular doesn't necessarily mean that these terms take an infinite limit, right? In fact, under suitable conditions, so these terms take finite limits. So let's not be scared about the word formally singular. It only means that we have to be extra careful with these terms. And so in order to include the conformal boundary, given this formally singular equation, so there are different proposals to do this, to reach the conformal boundary through an evolution problem. And I like to classify these different formulations according to the following, how they answer the following question. And the question is what to do with the conformal factor. So the first option is to say that the conformal factor is a given function of the coordinates, and then use suitable foliations, such as hyperboloidal foliations, and then just dealing with this formally singular equation. And long story short, if you do that, then you can land into what I call the hyperboloidal singular scribe fixed approach, just for the lack of a better name. But you all know which approach I'm referring to. Is this approach that was pioneered by Anil Senginoglu, Alex Baño, David Hilditch, Rodrigo Panoso Macedo, and many others. So we all know this formulation. And let me say, just for completeness, that this is not the only option. There are other options, kind of similar options. For instance, we have an approach which is being pioneered by David Hilditch and his numerical relativity group in Lisbon and collaborators in Jena, in which I have collaborated with them. And the idea there is not to make a conformal transformation. So the answer to this question is there's no conformal factor. Instead of that, you make chirurgical rescaling of the components of the metric in such a way that you can reduce as much as possible the number of formally singular terms. Nevertheless, despite all of our best efforts, there are still some singular terms in the equations. There's also, for completeness, let me say that there's yet another hyperboloidal formulation with a different flavor that was put forward by Rini and Moncrief, and also by Bardeen, Sarbach, and Bookman. And there also use some hyperboloids, but there you have not free evolution, but constrained evolution, and yet you still have some formally singular terms. Okay, so there's yet another formulation, which historically it was the first one to appear in this quest for obtaining a compactified version of the Einstein equations, and that's the formulation introduced by Helmut Friedrich in the 80s, and they go by the name the conformal Einstein equations. And the way this formulation answers to this question is to say that you have to evolve the conformal factor. You will see in a minute why that is the case. So the thing is that in order to regularize this equation, the price to pay is that you have to read this equation not as an equation for the unphysical metric, reading here second derivatives of the unphysical metric, but rather read it as an equation for the conformal factor. So an equation that says something like Hessian of the conformal factor is equal to some terms that have to do with the curvature. So the first price to be paid in order to regularize the equation is that now the conformal factor in general is a dynamical quantity that you evolve. And in addition, you have to introduce the curvature as an independent quantity that you have to evolve. So long story short, in the 80s, Helmut Friedrich obtained this set of equations which are formally regular in the sense that your eyes don't see this 1 over conformal factor term, and they can be thought as just a regular rendering of this formally singular equation. What are the variables appearing here? So we have the conformal factor, the Schouten tensor, which we can just simply think of it as the unphysical Ricci tensor. We have the Friedrich scalar, which is just a concomitant of the conformal factor, and importantly, we have the rescaled Weyl tensor, which is taking the conformal invariant Weyl tensor and dividing that by the conformal factor. And here the intuition is that we know that the Weyl tensor, there are certain conditions, they go to 0 at scri, and then if you divide by this conformal factor, you expect, but you don't assume, you expect that the rescaled Weyl tensor will go to something that is order 1 at the conformal boundary. Okay, so in the same way as in the Einstein equations, which are tensorial equations, these tensorial equations can be reduced to a set of PDEs, and there are different flavors of the different PDEs that you can get depending on your preferences. So if you like metric formulations, so in the menu we offer within the CEFEs to use generalized harmonic gauge, and if you do that, then you can get some nice wave equations for the metric components. If you are more of a tetrad or frame type of guy, then what you can do is to introduce a tetrad and use the first and second Cartan structure equations to append these equations to some equations for your tetrad. And in both cases, so no matter what you choose here, you will find that you need to evolve the conformal factor, right? So you have to solve this equation. Nevertheless, also for completeness, although I'm going to focus on this particular version of the equations, let me say that there exists another more general version of the conformal Einstein field equations, known as the extended conformal Einstein field equations, in which you complicate things a little bit to gain something. And that extra complication is that you have to use, instead of the Levi-Civita connection, you use Weyl connections, which is a non-metric connection. And what you gain from that complication is that allows you to adapt the gauge to some special curves known as conformal geodesics. And if you do that, what you gain is that essentially you can sort of trivialize this equation, because now if you evaluate the conformal factor along these curves, you find that psi triple dot is equal to 0. That means that this function is a quadratic function on tau. So this conformal factor is not longer an unknown. So now you know it explicitly. But I said know it in quotation marks because I want to bring to your attention some delicate point here. And is the following, that whenever we write a conformal transformation, we usually omit this pullback, which means just a change of coordinates. And the change of coordinates between the physical coordinates and the unphysical coordinates here is given through a set of ODEs. So more often than not, you cannot solve this set of ODEs in a simple, closed, explicit way. And I'm saying this to contrast this approach, that the fact that you know the conformal factor explicitly, since you don't know the coordinates, how the coordinates transform to each other, it's not easy to write a given background, say your favorite background, Schwarzschild, Kerr, or whatever. It's not easy to write those in an explicit way in this gauge. So you can do it in a sort of implicit way through this set of ODEs. And I'm saying this also to contrast this with one of the virtues, one of the many virtues of the hyperboloidal approach, in which there's a standard recipe in order to move from the physical to the unphysical coordinates, right? So there's a recipe that allows you to transform these t tilde r tilde coordinates, where t tilde equals 0 is a Cauchy slice, to this t equals 0 slice that ends at scribe, which we call hyperboloidal slice. You do it through this height function, which raises up this slice, and this compression function that allows you to compactify the hyperboloidal radial coordinate. But there's a price to be paid, as I said before. In the nonlinear setting, this approach leads to formally singular terms. And this something that it was a bit surprising to me when I started reading about the hyperboloidal approach is that when you go to the linear version of the equation, so the one that you use for quasi-normal modes, etc., it turns out that the final equation is formally regular. So you don't have this 1 over conformal factor terms in the linear equations. And it's obvious, well, I'll say it, that the linear hyperboloidal approach has been extremely successful as this series of seminars actually evidence. So we have from the calculation of very accurate quasi-normal modes to the very first calculation of the pseudo-spectrum. This was possible because my colleagues were doing this in hyperboloidal slices. So it has had a really big impact in linear black hole perturbation theory. Also, now there are some colleagues working on self-force calculations with this hyperboloidal approach. So it's quite prolific. And let me just say, in a short way, how is the approach here? So the idea is that you start from an effective linear physical equation, so the physical Teukolsky equation, or the physical Weyl equation, or you name it. And from there, following this recipe, you compactify that effective equation, and through this coordinate-based approach, you obtain a compactified equation on these hyperboloids. Okay, so what I'm going to talk about and what I've been talking about is kind of summarized in this diagram. So the story in this diagram goes like this. So here black lines mean compactification and blue lines mean linearization. So you start with the Einstein equations, the physical Einstein equations, and you compactify in whichever flavor you like. So either you compactify your equations allowing the conformal factor to be a dynamical quantity, and then you arrive to the conformal Einstein equations of Helmut Friedrich, which are formally regular. Or you give the conformal factor as a fixed given function of the coordinates, and then you arrive to a conformally singular Einstein equation, so which is formally singular. And that's on one side of the diagram. On the other side of the diagram, what you can do, if you are interested in the linear problem instead of the nonlinear problem, what you do is first you can linearize the physical Einstein equations and arrive to your effective linear equation called the physical Teukolsky equation or the physical Reggie-Wheeler equation. And once you are there, you do a compactification based on these hyperboloidal coordinates. So it's a coordinate-based compactification. And then you arrive to your Reggie-Wheeler or Teukolsky hyperboloidal equation, which is formally regular. And as I said before, something that surprised me to some extent is that the numerical hyperboloidal community that works mainly on this sector of the diagram. So one part of the community works with formally singular equations, and the other one works with formally regular equations. So I was a bit puzzled about it. So I wanted to investigate why these equations were formally regular from the point of view of the conformal Einstein equations. So the question was, are these hyperboloidal Teukolsky equation in any way related to the conformal Einstein equations? And I think this is not trivial because maybe it's more natural to connect these two. But connecting these two might be not so natural in the sense that these two formulations, although they have the same aim, they have the same purpose, they are based on fundamentally different philosophies. So what I wanted to see is if there was a relation between these two. Are these guys distant cousins? What is the missing link in this family tree? And this is what we found in this paper in collaboration with Rodrigo and Justin. So we found that the missing link, you can relate this, if you linearize the conformal Einstein field equations without imposing any particular coordinate system, so you arrive at what we call the conformal CFE Teukolsky equation, which is a general equation linearized from the CFEs that is not married to any coordinate system. And once you are there, you can choose to use any coordinate that you like and love. For instance, if you like hyperboloidal coordinates, which are adapted to scry, then this equation boils down to the hyperboloidal equation, Teukolsky equation that has been reported in the literature for quite a while, probably more than a decade. And that's providing a link to the CFEs. But also, as I said before, these equations are not married to any coordinate system. So if you prefer to use other coordinates, for instance, one thing that we did in this paper was to adapt this conformal Teukolsky equation to coordinates which are adapted to spatial infinity and null infinity. And then you find some Teukolsky equation, compactified Teukolsky equation, close to the cylinder at spatial infinity for the Kerr spacetime. So once you are
Edgar,
here,
can I ask sorry to interrupt, can I ask just a quick clarifying question there? When you
yes.
talk here about linearization, what background are you talking? Are you talking about Kerr explicitly there and only Kerr?
No. That's an important thing, right? So this Teukolsky equation is married to two things. It's only married. I'll say later what it is married to. But first, let me say
Okay,
what it's
then
not married to. It's
yeah,
not
that'll
married to
be quite.
Kerr. It's not married to Kerr. It's not married to Kerr. It's married to Petrov-type D. But there are many other spacetimes which are Petrov-type D and they are not Kerr. So this is not hinged on Kerr, nor hinged on any type of coordinates, right? Some of the derivations here, for instance, they have been done specifically for Kerr. This is not for Kerr, nor for any type of specific coordinate.
Thank you.
Well, thanks for your question because it's a point that I want to emphasize. So I just finished this thing of the diagram saying that now in this family tree, so we can claim some relation in this family tree from these, say, grandfathers to this grandson through this intermediate step, right? Okay, so how this story starts is that, well, looking at the conformal Einstein field equations, I noticed that despite the fact that the nonlinear problem has been studied quite a lot, the linear perturbations had not been studied so much as the nonlinear case. And so with Justin, we decided to look at the linearization of the conformal Einstein field equations, first in a general background and then on a Minkowski background. And of course, this is not completely new because in the conformal Einstein field equations community, which I come from, if you think linearization a la Penrose, in which it's a non-metric approach in which your linear equations look like this the spin to equation for this Weyl spinor, right? And if you compare this formulation of the linearization of the Einstein field equation, this doesn't look at all similar to the standard discussion of linearizations that are presented, for instance, in many textbooks, like Majore, for instance. So we decided to put things in a language in which was closer to the standard literature. Say, making a linearization a la Einstein or a la de Donder, or if you want, a la Majore, in which you split the metric into a background metric, ring, so ring means background, plus check, which is a perturbation. You do that for not only the physical metric, but for all the fields, in particular for the conformal factor, right? So this is the perturbation to the conformal factor. And essentially what we did was to linearize a particular flavor of the conformal Einstein equations, a particular flavor of a hyperbolic reduction of the conformal Einstein equations, which is the one that I was telling you before, the one that renders wave equations for the metric. And this was obtained by Paetz in 2013 and then refined by Carranza, Hurset, and Valiente in 2019. And you can think of it as the equivalent of generalized of harmonic gauge in the Einstein equations, but done for now the conformal Einstein equations. This was done by these guys. And what Justin and I did was simply taking those equations and linearizing it. And instead of having, for instance, the generalized harmonic gauge, you use the generalized Lorentz gauge. But there's like a mapping between this nonlinear flavor of the equations and this linear version of this equation, right? In the same way, there's a natural mapping between this linear version of the equations and other formulations of the conformal Einstein equations based on spinors. Anyway, at the end of the day, of course, because we follow this approach, you find a set of wave equations for your perturbations. So your metric perturbation, here this is a source, and all of the other fields. And the thing I want to bring to your attention is that the equation for the perturbation of the rescaled Weyl tensor has a source, which if you assume that your background is Minkowski, or conformally Minkowski, I should say, conformally flat, then this source becomes 0. And that means that your system of equations decouple, right? So the Bianchi system decouples from the rest of the equation, right? Which is something expected from this other version of the equation, right? So this is something that we expected. And well, this is what I'm saying here. And now the question is, okay, if you don't want to linearize around Minkowski or around a flat, conformally flat spacetime, then what happens? So if the background rescaled Weyl tensor is different from 0, hell breaks loose, and you have a coupling between everything. So this is expected. And something that I want to emphasize from this coupling is that not only this is the trace-free Ricci on physical trace-free Ricci, and this is the on physical perturbation to the metric. So not only these perturbations couple, but also the perturbations to the conformal factor. So what we want to see is if you specify the background in a different way that is not so trivial as this, if this expression simplifies or not, right? So whether this expression, for instance, simplifies for Schwarzschild or for Kerr or for any of our favorite black hole spacetimes. But seeing the equation in this form is not very illustrative, so we don't know how this decoupling could happen. And even if we have the evidence from the physical case that there should be a decoupling because of the Teukolsky equation, here is not obvious because in the physical equations, there doesn't exist the conformal factor, the perturbation of the conformal factor. And here we have this coupling with the conformal factor. So it could happen that because of the presence of the conformal factor, the magical decoupling between the Bianchi system and the rest of the equation doesn't happen, right? So something there has to happen so that this guy decouples. And this is the main point of the story, and this is what we did. So instead of specifying a particular background, and this is going in the direction of answering David's question, so instead of specifying a specific background, what we say is let's just specify that the background is algebraic special. Let's say that is Petrov-type D. And that's what actually Teukolsky did originally. So in his original paper, Teukolsky didn't derive his equation just for Kerr. He derived it for any Petrov-type D background, right? So it can be Kerr or whichever Petrov-type D background that you like and love. So what we did was essentially printing Teukolsky's paper and then saying, let's just follow his steps, but instead of doing things with the Einstein equation, let's repeat the calculation with the conformal Einstein equation. So following Teukolsky, the calculation starts from writing your beloved equation, in this case, the conformal Einstein equations, in Newman-Penrose form, which thankfully this work has been done by Juan, David, and Peng in 2020, and the equations schematically look like this. So again, I emphasize that the conformal factor is a dynamical quantity. It satisfies some equations, And these equations in box, this is the Bianchi identities, this is the Bianchi system, and this is the second Cartan structure equation. And here notice everything on physical. And here notice that the conformal factor enters here, right? So it could be that this coupling makes a mess, right? And at the end, you cannot decouple the equations. So this is essentially the calculation to be done. And let me also emphasize that this phi is the rescaled Weyl tensor. So it's not the unphysical Weyl tensor, it's the rescaled Weyl tensor, right? So there's an extra power in the conformal factor there. Okay, so following the strategy of Teukolsky, so we assume first that the background physical spacetime is Petrov-type D, and then you have to transform this into a statement for your unphysical background manifold. And it's pretty obvious that if the background spacetime is Petrov-type D, then the unphysical background spacetime is going to be Petrov-type D. But there's a subtlety there, and is that if your tetrad is not aligned to the principal null direction, either in the physical or in the unphysical setup, then the vanishing of some of your rescaled Weyl components or your Weyl components will not happen, right? So in order to have, so Petrov-type D is a geometric condition that doesn't depend on your tetrad to be a specific tetrad aligned to the principal null directions. But if you want certain components to be zero, that is possible if you align the tetrad to your principal null directions that are guaranteed to exist for a Petrov-type D spacetime. So what we require, and this is also answering David's question, the thing that we are marrying to is that the unphysical tetrad is aligned to the principal null directions in the same way that you assume that the physical tetrad is aligned to the principal null directions. We do that because then these guys vanish, and also some spin coefficients vanish. And the fact that these guys vanish is more or less obvious because of the conformal transformation of Weyl, but the way the spin coefficients transform is not trivial, right? So magically, these spin coefficients are conformal densities. So the vanishing of these coefficients in the physical setup mean they vanish also in the unphysical setup. And this is one of the ingredients that we need in order to simplify some of these equations. So under that Petrov-type D background, so this assumption, the equations, some of a sector of the equations simplify to this. So this is the starting point. So these two equations are coming from the Bianchi system, and this is coming from the second Cartan structure equation. And these are the nonlinear equations, right? So notice that this term in red contains the conformal factor, right? So here's where the coupling with the conformal factor can appear. So let's linearize these equations. So I'm going to focus only on this term. So if you expand this conformal factor, you'll get something that is background conformal. Yes, of course.
Hi, Edgar. It's Jahanur. Yeah, so
Hello.
yeah, so understand this. I'm understanding correctly. So when you say that that your physical background metric, and so this ring means your physical background metric, right? Tilde.
So tilde means physical and ring means background, right?
Yeah.
So this
So
is the physical background metric.
yeah, so then so I understand for the full metric how you transform the all quantity in terms of unphysical one. So it is just definition is omega square g, right?
Yeah.
So
Yeah.
how you decompose, when you decompose background and perturbation, then what is your definition of unphysical background? So I understand.
Yeah. So let me write it
Background.
here. So yeah, that's a very good question. So the idea is that for the background, so for the background, you say background conformal factor is equal to background on physical metric. And
This
for
is
the
the
no, for
okay.
the other one is so this guy is this guy plus this. So for this one, this is a more complicated combination, right? Because you say this guy is this
Yes.
thing, this guy, and this splits into background conformal factor plus perturbation if you stay to linear order, and this guy splits into background conformal factor plus perturbation physical, right? So you have to expand this thing out, right? So that's the definition, right? So it's not that we say, oh, immediately this guy is this guy square.
Yeah,
No.
I mean, I understand background can be rescaled like omega square, but the rescaling of the, how do you rescale the perturbation of physical and unphysical one?
Yeah, you simply have to expand this thing out, right? You just
Okay.
expand this thing out, and that will give you the relation between this guy and this guy, right? So you just
Okay.
expand this thing out and to the order that you want, right? But what you are saying is very true. So one has to be careful of these kind of mixed terms. Yeah. So actually, those details in this paper we didn't put too much details on that because that is contained in this paper of with Justin. So there we do that calculation that you are saying very carefully, not only for the metric but for all of the other fields, which actually is more complicated. So yeah, you're right. One has to be careful in that. But for the background metric, this is the relation. So for the background metric is super easy. For the
Okay.
perturbation, not so much.
Okay. Okay. Thanks.
Okay, so yeah, because for the background is very easy, is that well these conditions transform so nicely. But this is for the full nonlinear thing, right? For instance, here I'm going to expand this product. So this guy is going to contain the background conformal factor plus a counter times the first order perturbation, then counter square times second order perturbation plus etc. Then this phi naught is phi naught background plus first order perturbation to phi naught, second order perturbation to phi naught, etc. Right? So you expand this thing out. When you expand this thing out, because this guy is zero by virtue of the physical space and being Petrov background, physical background being Petrov-type D, because of virtue of this, is that when you expand this thing out, the linear term only appears with the background conformal factor. So the perturbation of phi naught comes multiplied by the background conformal factor. Okay, then you go to next order. In the next order, you have epsilon square. Then you have a coupling between the perturbation of the conformal factor and the perturbation of phi naught, and so on and so forth. So this is to say, if you stay to linear order, so if you ignore all of these terms and you stay here, then there's a decoupling, right? So in the Bianchi system, by virtue of being Petrov-type D and the linearization, there's this decoupling between the perturbations of the conformal factor and the perturbations of Weyl. And this is ultimately what allows to make contact with the hyperboloidal Teukolsky equation, right? But let me just emphasize that if you were to go to second order, then there would necessarily have to be a difference because here we have perturbations, necessarily the perturbation of the conformal factor enters in the CFE approach, but in the conformal singular approach, well, in the conformal approach, hyperboloidal approach, the conformal factor is never a dynamical quantity. It's not, doesn't solve any particular equation. It's given by a fixed expression in terms of your coordinates. So there's no perturbation of the conformal factor. So if you were to go second order in hyperboloidal, there would never be a coupling with the conformal factor because the perturbation of the conformal factor never appears. However, if you do it CFEs, at second order, there will be a coupling. So that's one thing that I wanted to emphasize. Okay, so once you do this calculation, well, you follow Teukolsky steps, and then the work is just to check that at every step you take, whenever the conformal factor enters, the conformal factor doesn't messes up the decoupling, right? Because it always has the potential to mess up this decoupling. So long story short, the conformal factor to linear order doesn't messes up the coupling, and you end up with this equation that is not married to any particular coordinate system, is only married to a null tetrad aligned to the principal null directions. And this is formally identical to the Teukolsky equation, just with all the fields here being non-physical, and this guy here, the background conformal factor appearing here. So this is something different. And the field that we are looking at is not the unphysical Weyl, but rather the rescaled Weyl components. And this equation, as I said before, is married to the principal null direction, but not any particular coordinate system. And even in the frame, we have some freedom. We have the freedom to do a spin boost transformation, right? And to show that here, I'm showing you how the perturbation of the physical perturbation of Weyl connects with the physical perturbations of Weyl, right? So you have some conformal factor to some power, and this omega tells you the freedom that you have in putting different weights in the in your legs of your tetrad. So there's some freedom there, and also the freedom of making a spin boost transformation, because a spin boost transformation of the tetrad will not mess up with your principal null direction. But for instance, you're not allowed to do a null rotation, because a null rotation messes up with your principal null direction. So this is the main result. And I'm almost done here. So this is what we obtained. And as I said, this is not married to any particular coordinate system. But when you choose a particular coordinate system that you like, then you may land on known cases or new cases. For instance, if you choose your background to be Kerr, which is a particular case of a Petrov-type D, and you choose your coordinates to be hyperboloidal, then this conformal Teukolsky equation reduces to the hyperboloidal Teukolsky equation that has been reported in the literature for quite a while, in the works of Anil, Rodrigo, Jose Luis, and many others. But let me remind you that the equations in those papers were obtained through a different method, an effective coordinate-based approach. Okay, but if you choose a different coordinate system, for instance, you can choose coordinates which are adapted to the geometry of spatial infinity, also fix the background to be Kerr, and then you can obtain a new result, right? What we did was to take the coordinates introduced by Jörg and Rodrigo in 2021, which are some coordinates for the Kerr spacetime adapted to spatial infinity, which make a blow up of spatial infinity. And here I want to say that this cylinder at spatial infinity is not Friedrich's cylinder, because Friedrich's cylinder, for those of you which work on this Friedrich cylinder is based on conformal geodesics, and these coordinates introduced by Jörg and Rodrigo are not based on conformal geodesics. Nevertheless, they do the job, which is to blow up spatial infinity to a cylinder which is total characteristic. And this is evidenced also by the fact that when you compute this conformal Teukolsky equation, you specify these coordinates, you find equations that when you evaluate them at the cylinder, you obtain transport equations at the cylinder. So these coordinates do the job, despite the fact that they are not based on conformal geodesics. Okay, and these equations are there for the taking to be analyzed, and maybe if we analyze these equations, we can say something about perturbations of Kerr close to spatial and null infinity. Okay, so now I'm going to conclude. So the conclusions is that in this work, we show a bridge, or rather a contention. So the linear hyperboloidal Teukolsky, or the linear hyperboloidal Reggie-Wheeler equation, the linear hyperboloidal approach, is contained as a particular case of the linearized conformal Einstein equations, because this decoupling happens at the linear level and for Petrov-type D spacetimes. Nevertheless, as I said before, I want to emphasize that there's a gap, because as I showed before, if you go second order hyperboloidal, or if you leave Petrov-type D, then it's clear that the effective equation that you obtain in the hyperboloidal approach to second order or higher order is not going to coincide with that of derived from the conformal Einstein equations. So the magic happens at the linear level and for Petrov-type D. Okay, so perspective of this future work. So of course, one thing that we are ignoring completely is metric reconstruction, right? That's a big point in the to-do list, because the only thing we show is that for Petrov-type D backgrounds and at the linear level, there's this decoupling, right? Of the Bianchi system from the metric system, and then we ignore the metric system and focus on the Bianchi system, right? So a more complete analysis would be to make a metric reconstruction, right? Another possible route to extend this work is go beyond linear perturbations. Also, one thing that I want to do is to rederive this equation using more technology. Instead of using Newman-Penrose, using the conformal GHP formalism. And the reason for doing this is not just for repeating the calculation one more time, is just because with this more powerful formalism, it will allow us to first obtain a more clear, crystal clear geometrical understanding of the calculation. And also, in this calculation, these are the Teukolsky equations for the variable, for the perturbations, not for the master variable. Actually, in our work, to find the master variable, you have to multiply these guys by some factor that has to do with the killing spin or living on Petrov-type D spacetimes. And if you do that, then this equation sort of becomes a mess, right? You can do it, and on coordinates, it is what it is. But that approach is not so elegant. It's effective, it works, but it's not so elegant. So in this aim for obtaining something more clear, so we could use the conformal GHP formulation to obtain directly conformal Teukolsky equation for directly the master variable, not for the raw variables. That's one thing. Also, we could go beyond Petrov-type D. There's in the literature something called the universal Teukolsky equation, which is a massaging of the Bianchi system in such a way that when you specify your background to be Petrov-type D, it boils down to Teukolsky. But actually, those equations hold for any type of background. And all of this is going in the direction of trying to develop a full linear black hole perturbation theory in the framework of the conformal Einstein field equations, a little bit inspired by the success of the hyperboloidal approach in the linear black hole perturbation theory. So I believe that one could follow a similar program, hinged not on necessarily on hyperboloids, but more generally on the conformal Einstein field equations, which are in principle not married to any type of coordinate, as shown with the cylinder. And that's pretty much it. Thank you.
Thank you, Edgar, for this beautiful summary and overview of all of your work. I don't know if Anil is there to actually stop